Chapter 3, Section 2, The Structure of Atoms. So let's talk about where we left off. So the last time we talked, we mentioned that the atom was a solid ball, and this is based on Dalton's ideas about the atom. So what we're going to do in this section is look at some experiments that were done, the observations that were made, and then the conclusion about the atom that was drawn from that. So the first experiment we're going to look at is called the cathode ray tube experiment. It was conducted by J.J. Thomson. Okay. So what we have is a gas tube. Inside, the gases are at a very low pressure because you can see it's connected to a vacuum pump. Okay. It's connected to a battery. And the inside of this is kind of coated with a zinc sulfide, which allows it to fluoresce when electrons move through it. Okay, so what we're going to do is listen to the animation, and then we're going to talk about the observations that were made and the conclusions that he made based upon his discovery.
When the cathode and anode of a cathode ray tube are connected to a voltage source, electric current flows through the tube and can be seen as a cathode ray. The cathode ray is made up of electrons. When a positive electric field is placed next to the tube, the path of the electrons moves toward the field. Using the strength of the electric field and the amount of deflection, J.J. Thomson was able to calculate the ratio of the charge of electrons to the mass of electrons. Imagine a baseball player throwing a ball. Like the cathode ray, with no outside influences, the ball goes straight when the baseball player throws it. A strong wind, however, could blow the ball and make it go off course. An outside positive field attracts the electrons in the cathode tube and makes them go off course. If the baseball player threw a lightweight plastic ball instead of a regular baseball, the wind's effect would be even more evident. The mass of the ball is one of the factors that determines the path the ball will take. Similarly, if the wind were stronger and the baseball player used the original ball, the wind's effect would be more evident. The strength of the outside force is one of the factors that determines the path the ball will take. By observing the path of electrons in the cathode tube, Thomson was able to calculate the ratio of charge to mass of an electron.
Okay, so let's talk about his observations that were mentioned in the animation. He says that the cathode rays are deflected by a magnetic field. They are deflected from a negatively charged object, and that the charge to mass ratio is always the same for the cathode rays. So based upon these observations, he made the following conclusion. He said that cathode rays are composed of negatively charged particles, and he called them electrons. So now we have this solid ball, and now we know from Thomson that there are smaller particles in the atom. So this has disproved part number 1 of Dalton's atomic theory. So based upon his observations and conclusions, he made some inferences about the atom. He says that atoms are neutral, so there must be a positive charge. Okay, so that everything equals out. So the amount of positive and negative charge would be equal to each other. Electrons are so small, so that means they have very little mass, that there has to be some other particles that contribute to the mass of an atom. The positively charged particles are one of them, but the other particle that he's referring to are the neutrons. It is the neutrons that can differ from atoms of the same element that creates isotopes, which disproves another part of Dalton's atomic theory. So now we have a new picture of the model of the atom, and it is called the plum pudding model. So based upon Thomson, he says that we have this ball of positive charge, and there are negative particles embedded within it. It was referred to as the plum pudding model. So plum pudding kind of looks like this, so you can kind of see where the chunky pieces are supposed to be representing electrons. Okay. Can also think of it as a watermelon, that those little black seeds are representing electrons. After Thomson, a scientist by the name of Ernest Rutherford and his associates conducted the gold foil experiment. And his hypothesis is based upon Thomson's experiment. And he says this: alpha particles, these alpha particles are positively charged, would pass through with slight deflection. Okay. In other words, since it's this positive ball, those electrons would just pass right through, or those alpha particles would pass right through. But his observation was really this: there was only 1 in 8,000 that were actually deflected back to the source. So that one particle that was deflected had to hit something that was densely packed and had a positive charge. So he says this. He says the atom contains a small, densely packed bundle of matter with a positive charge, and he named that the nucleus. Okay. So let's kind of look at the structure of an alpha particle. Okay. So an alpha particle basically has a +2 charge because it has 2 protons. Okay, so let's look at the experiment for Ernest Rutherford. So the box that you see here is the source of those alpha particles. The ring around it was coated in zinc sulfide, so if anything struck it, it would make a mark so that they could record where the alpha particles were deflected to. And then it's called the gold foil experiment because it used a very thin sheet of gold foil to beam the alpha particles at.
With Hans Geiger and Ernest Marsden, discovered the nucleus of the atom using a beam of positively charged alpha particles. They bombarded a sheet of gold foil with a stream of alpha particles. Most of the particles passed straight through the foil. About 1 in 8,000 particles, however, were deflected, sometimes directly back at the source. Rutherford explained these results by hypothesizing that nearly all of the mass of an atom is concentrated in a very small volume called the nucleus. If the nucleus were small, it would be easy to miss. Alpha particles which miss the nucleus are deflected only slightly, if at all. Alpha particles which hit the nucleus are deflected severely.
So here are the results of Ernest Rutherford's gold foil experiment. You can see that most of them pass straight through, which confirms that the atom is mostly empty space. And it was only those few alpha particles that would actually hit that small, dense bundle of matter, the nucleus, that would actually be deflected. Okay. Chapter 3, Section 3, Electron Configuration. This is going to continue our exploration of atomic theory. So after Ernest Rutherford, a scientist, actually a physicist by the name of Niels Bohr, conducted an experiment in which he observed that if he took a tube of hydrogen gas and passed electric current through it, and that light was passed through a prism, we would get a line emission spectrum. Okay. So according to Niels Bohr, we have this nucleus that has protons and neutrons in it, so just like Rutherford. But now what Bohr is starting to do is help us define what that cloud around the nucleus looks like and how the electrons are arranged. So according to Bohr's model, electrons can only be certain distances from the nucleus. And it's based upon those colors of line and how they have a specific wavelength, a specific frequency, and a specific energy. Each distance corresponds to a certain quantity of energy that electron can have. And so the closer to the nucleus an electron is, it would have a lower energy, so that energy level would be lower. The farther from the nucleus, the more energy it has. And that energy level would have a greater amount of energy. And you can refer to figure 16 on page 91. So before Niels Bohr, Rutherford had proposed electron orbits. But the way his orbits were described is that electrons revolve around the nucleus in a circular or elliptical orbits, just like the planets orbit around the sun. And if we're thinking about this, we know that electrons are negatively charged and protons are positively charged. We also know from earlier exploration in science that opposite charges attract each other. So what we would expect to see is that electrons being attracted to the nucleus. Okay, and that's not what's happening. So Rutherford's model is pictured on page 90 on figure 15, and then Niels Bohr's model is pictured on page 91, figure 16. So here's our picture of Niels Bohr, and he referred to those places around the nucleus where electrons are located as orbits. He says that each orbit has a fixed energy. He says that lower energy orbits are closer to the nucleus. And it's not possible for electrons to exist in between the orbits. Now, we're going to hold true to this idea that there are orbits around the nucleus, but we're going to refine this a little bit in some lecture that we're going to do in class. But let's begin to look at this last model of the atom. Okay, so we started with Dalton. We talked about Thomson. We've talked about Rutherford. We've talked about Bohr's model, and we've looked at all pictures of all of them. So our current model of the atom is referred to as the quantum model of the atom, and it believes that electrons act like both particles and waves. De Broglie suggested that electrons could be considered waves confined to the space around a nucleus. Okay. And we kind of get this wave idea from the fact that we can get this line emission spectrum. We get the idea that they behave like particles because of things such as diffraction, which is something that you'll spend more time looking at in physics class. So again, as waves, electrons could only have certain frequencies which correspond to specific energy levels. Okay. So in the quantum model, we say electrons are located in orbitals, which are regions around a nucleus that correspond to specific energy levels. Okay. Orbitals are sometimes called electron clouds because they do not have sharp boundaries. Okay. And we're going to kind of get a view of these orbitals overlapping when we start looking at bonding in later chapters. We're going to look at these electron clouds, though, in class, and we're going to give names to all of these orbitals.